So we need to find the magnetic force first on each of the four sides of the loop for part A of this problem. Now, for the long straight wire, the right-hand rule tells us that the magnetic field from the long straight wire is coming out of the page. If I point my thumb in the direction of I1, my fingers curl around and come out of the page. So that is the magnetic field that the loop is immersed in. So the right-hand rule tells us for part A that the magnetic force is Li cross B, and that will be I2 B1, right? It's the current I2 crossed into the magnetic field that it is immersed in from wire 1. So we use the palm thumb finger rule to get the direction. If I point my thumb in the direction of I2 on this bottom wire, and I point my fingers in the direction of the external magnetic field, then my palm points up like this. So there's the force. Over here, the force points to the right. Up here, the force points down. Right, everywhere in this loop, it points inward. So there's my magnetic force on each of the four wires. Now, for part B, we need to find out the net magnetic force on the loop. So the magnetic force on the left-hand side of the loop is equal and opposite to the magnetic force on the right-hand side of the loop. Okay, both of those segments of wire are the same length, they carry the same current, and they are being exposed to the same external magnetic field from wire 1. So they cancel, and we can ignore them. The same cannot be said for the top and the bottom, right? The magnetic force on the bottom wire is greater than the magnetic force on the top wire, because B1 is stronger when we are closer to I1. So I'm going to have to combine those. I'll use my standard Cartesian sign convention, I guess, that up is positive, right? So the total force is going to be plus the force on the bottom wire minus the force on the top wire, right? Because the bottom wire points up, so there's the magnitude and direction of the bottom wire, and the force on the top wire points down, so there's the magnitude and direction of that. Alright, so the magnetic field, well, you know what? Let me just do it this way. The magnetic force on the bottom wire is equal to Li2 times B1 times sine 90, right? Now L is 0.16. That's how long that wire is, right? That's up here. I loop is 0.35. That's the current in the loop. And now the magnetic field on the bottom wire, that's given by mu naught times 5.0, I1, divided by 2 pi, and then we're 6 centimeters away from I1 here. Okay, so if I multiply all those numbers out, I get 9.3 times 10 to the minus 7, and that's in the plus y direction. Now if we do a similar calculation for the top, Li2 B1 on top, sine 90, then that is 0.16 times 0.35, and then it's mu naught times 5.0, but now the distance to the top wire is 14 centimeters, right? It's 6 plus 8. That works out to be 4.0 times 10 to the minus 7 in the minus y direction. So the total force is plus 9.3 minus 4.0, which is plus 5.3 times 10 to the minus 7 newtons, or if you want to be more precise about it, it's 5.3 times 10 to the minus 7 newtons in the plus y direction.